Good morning. So we didn't quite finish 1B last time, so just to recap, we did quite a bit in the section, but where I want to start today is coming back to these sufficient conditions for congruence of triangles, which was these SSS conditions. If you know all three sides are congruent, then the triangles must be congruent. If you know two sides and the angle between them are congruent, then the two triangles must be congruent, and so on. But you'll notice I don't have every single permutation of S and A up here. So what about the others? What about say AAA? So what if you know you have two triangles where all three angles are the same? Does that guarantee congruence of triangles? Why not? Just give me an example of something.
If you cut all the lengths like in half for the next triangle.
Exactly, yeah, so you can scale it, right? And the answer is obviously no, that's why it's not listed in this first four. But no, just do something like, so your suggestion was take one triangle and then cut all the lengths in half, so go with the scaling of 1/2 of that original triangle, where all of these angles are congruent to each other. And there you go. AAA is satisfied here, but these aren't congruent triangles. They're what's called similar triangles, and we'll talk about that soon enough, but they're not congruent, so you can just rescale. Scalings satisfy AAA. And what about SSA? I think it's the sixth permutation that we haven't discussed. And the answer here is also no. It's a little bit harder to come up with an example, but I'll show you. So again, no. And here's the typical picture that's given. This is a little bit long here. Go with a triangle like this. So I'll go A, B, C. And what I'm going to do is I'm going to imagine, in fact I'll just draw this second triangle right on top of this one. Imagine this side is sort of on a hinge. All right, so I'm going to pick up this side and I'm going to hinge it this way and draw a second triangle right on top of it, where this side has the same length as that side. And I'll call this triangle ABD. So that side and that side should have the same length. In these two triangles, these two sides match up, so they have the same length. And this angle right here in both triangles match up. Okay, so I have two different triangles sort of drawn on top of each other, where AC is the same length as AD. AB is the same length as AB in both of them. And angle B is the same as angle B. So these two triangles do satisfy SSA, right? Side, side, angle. And yet they're not congruent. But they're not, let's see, what am I calling this? ABC is not congruent to ABD. And so there's a typical failing case for SSA is you sort of think of having this leg over here, this arm, on a hinge. So keep the length the same, but twist it inwards or outwards. Now it turns out that the reason it failed, though, is because I'm not looking at right triangles here. If you restrict yourself to just right triangles, then SSA is actually enough, and it's a special case that's known as the hypotenuse leg theorem. Again, Again, usually I would just go onto that board, but the camera's not going to catch it, so I'll have to stick to this one. So here is the famous hypotenuse leg theorem, which essentially is SSA, but only for right triangles. By the way, our textbook calls this the hypotenuse arm theorem, which is fine. Referring to legs as arms of triangles is kind of typical. But I was curious, I Googled this because I've never heard it called the hypotenuse arm theorem, and Google says no one calls it that either. So I'm just gonna overrule our textbook here. And it says the following. It says if two right triangles have hypotenuses of equal length, so equal hypotenuses, and a leg of one triangle equals a leg of another, again, being a little bit lazy with the language here, when I say a leg is equal to another one, I mean its measure, right, its length. Is equal to a leg of the other, then the triangles are congruent. And the legs of right triangles are just non-hypotenuse sides. They're non-hypotenuse sides. Alright, so all this is saying is if I have two right triangles, where the hypotenuses are the same length, and I know that one of these legs has the same length as another leg, I'm not even going to draw the same legs there, then they must be congruent, which means for right triangles, SSA is actually a condition, right? That's why this is SSA for right triangles. And one very obvious proof, if you already accept hypotenuses theorem as being true, right, a squared plus b squared equals c squared, well, if the hypotenuses are the same length and the two of these legs have the same length, then obviously the third legs must have the same lengths. And then SSS says these are guaranteed to be congruent. But we don't have that yet, so we'll write a separate proof. Any questions so far? Okay. I think this is only the second proof we've done in this class. So, we'll of course start with two triangles that meet our hypotheses. So let ABC and triangle DEF be right triangles with let's put our right angles at A and D. Right angles at A and D and suppose, I'm going to draw a picture of exactly how I'm labeling things here in a second, but suppose that the following sides are the same lengths. Suppose BC has the same length as EF, and AC has the same length as DF. Okay. So, two triangles, A, B, C. This first one has the right angle at A. And another triangle, DEF. This one has the right angle at D. And we've said, okay, side BC, the hypotenuse here, has the same length as side EF. The hypotenuse there. And this vertical leg AC is congruent to this vertical leg DF. By the way, again, notationally, when I write an equal sign, it's clear that I'm talking about the lengths of these sides, but I could have just as well written that for congruence. And now it's the actual physical side, the line segment, BC, is congruent to the line segment EF, which means they have the same length. Okay, so there's our hypotheses. Nothing, we haven't actually started the proof yet. We've just written out our hypotheses. What I'm going to do, this is something that Euclid does a lot in his proofs, and again, he really needs to axiomatize that he can do this. It's this superposition principle. I'm just going to allow myself to freely move this triangle around. I'm going to allow myself to freely move this triangle around, and what I'm going to do is I'm going to flip it over and move it over so that this side DF matches up with this side AC. Alright, so I'm just going to reposition that triangle so that it lives over here. So let's see, that was A, what do we have, DF, there's D, there's F, those two vertices just match up now. There's E. So we'll write that down in the proof. Move the triangle DEF so that points A and D and C and F coincide. And in 1899, when Hilbert came along and did geometry sort of rigorously and properly, he did include this as one of his axioms. This is, you're allowed to move stuff around in the plane as long as you're not resizing your triangles or anything. Well, what now? Now I'm going to think of this whole thing as just one triangle. So the triangle EBC. I'm just going to choose the vertex C instead of F. It's the same thing. I'm going to consider this triangle EBC. What type of triangle is that? It's isosceles, right? And we have a theorem about isosceles triangles that these two base angles should be congruent. Right, so these coincide. Let's see, how do I want to write this? Since triangle EBC is isosceles, in fact, I'm not going to invoke the fact that those base angles are the same. What I'm going to do is I'm going to invoke this, and this side AC is the altitude, from vertex C So it's absolutely true that these two base angles are equal to each other, but I think the fastest way to wrap up this proof is actually going this other route. Right, this is a right angle right here, and this is a right angle right here. So since I've got a straight line drawn from this peak vertex that cuts through perpendicularly to the base, that's the definition of being an altitude. And we showed last time that for isosceles triangles, altitudes are also bisectors, right? So this altitude bisects this angle C. Is the altitude from vertex C. It is also a bisector of this angle ECB. Right? What does that mean? That means that these two angles here are congruent, because they're both just half of this original angle. Right? So thus, angle EFD is equal in measure to this angle BCA. And I think that does it for us. Now I just want to conclude that this triangle is congruent to this triangle. Why can I do that now? Yeah, side angle side. In fact, by the way, part of our hypotheses were already that these two angles here were congruent, so I didn't need to invoke that using the isosceles triangle theorem. Once I know that these two are congruent, now I can say side, angle, side, and side, angle, side. So by SAS, it follows that the two triangles we started with are congruent. The triangle ABC is congruent to triangle, and I'll be careful here to get everything in the right order. A corresponds to this vertex D. B corresponds to the vertex E. And C corresponds to F. Which is what we wanted to prove. So again, this is sort of what proofs look like, right? There are these sequences of logical statements, one following from the next. And this is a fairly short proof. We haven't made many jumps here. The first line is just writing down our hypotheses, making sure everything matches up as they should with our labeling schemes and whatnot. And the only jump here, the trick is actually moving our triangles, right? Taking our two triangles and creating a single isosceles triangle out of them. And with that, well, we've already observed that altitudes and bisectors are the same thing for isosceles triangles, so we have congruence of that angle and that angle. Any questions? Awesome. So our next section is really short and should just be some language review for you, really. There's not a whole lot to it. It's basically just naming some angles and whatnot. But let's see. So section 1C in the textbook. In fact, it's so short that there's not even any problems in the textbook associated to this section, but angles and lines. So I guess first things first is what's a transversal. A transversal is a line that intersects two given lines. And there's one particular case I want to avoid. Here's my two given lines, right? This would be a transversal, this would be a transversal. What I don't want to have is a transversal that cuts through right there at the point of intersection. So I'll specify intersects two given lines at two distinct points. All right, and forcing it to cut through at two distinct points, two different points, means it can't cut through at that point of intersection. So transversal typically looks like, and nothing in my definition here requires that these two lines are parallel, but I'll draw them like this because it's easier to see later on what's happening. So two given lines R and S, and my transversal there is T. Okay, so this creates a whole bunch of angles. Alright, so this gives us a whole bunch of angles, and I'll just label these sequentially. Here's angle 1, 2, 3, 4, 5, 5, 6, 7, 8. Alright, this gives us a whole bunch of angles, and for starters, let's point out that these angles here that I've circled first, 1, 2, 8, and 7, those are usually called interior angles. Why? Well, because they're on the interior of these two given lines. So these are interior angles. And these two outside angles, or rather 4 outside angles, 4, 3, 5, and 6, those are exterior angles. Okay, so a whole bunch of terminology now. This creates really several pairs of angles. And I'm not going to name them all, but I'll name the most popular ones. So first up, we've got corresponding angles. All right, so let's see. These are angles that are on the same side of a traversal. Same side of the traversal, and on corresponding sides. That's a nice way to write it, I think. Corresponding sides of the given lines. Okay, so for example, angle, I'm going to destroy my picture here by circling a whole bunch of angles. Angle 1 is sort of below this first given line. So if I want the corresponding angle, I would look below the second given line and on the same side of my traversal. So angle 1 and angle 5 are corresponding angles. Right? So for example, angle 1 and angle 5. And we'll just do one more pair here. There's of course 4 of them, but how about angle 3? That's above my first given line, so I'm going to look on the same side of my traversal and above the other line. So angle 3 and angle 7. Those are corresponding angles. Etc. There's 2 more pairs there. All right. 2 and 6, and 4 and 8. Next up, we've got alternating angles, and these come in 2 different flavors, either interior alternating angles or exterior alternating angles. So we'll do, usually write as alternate interior angles. And alternate exterior angles. There we go. So for starters, alternate interior angles have to be interior. So these will be opposite sides of the transversal and interior. Opposite sides of the transversal plus interior. So I'm looking for interior angles which are 1, 2, 8, and 7, and that are also sort of on opposite sides of the transversal. So if I choose 1, for example, the paired up angle with that would have to be interior and opposite on the opposite sides of the transversal. So 1 and 7 are alternate interior angles. For example, 1 and 7. And I only have one other pair here, which is choose 2, and now everything's just circled, but 2, I need to be interior and on the opposite side of the transversal, 2 and 8. 2 and 8. All right, meanwhile, alternate exterior angles are the same thing, opposite sides of the transversal, but exterior. So, opposite sides of the transversal, but exterior. Again, I hate the way our textbook sort of describes what these angles are, because they never bother to tell you what exterior and internal angles or interior angles are. And it makes describing exactly what these are sort of a bit of a nightmare. So I think once you have interior and exterior figured out, it's a lot easier to describe these angles. So let's see, I'll choose 1, 4. What's the corresponding alternate exterior angle for 4? Yeah, 6, right? Got to be exterior and on the opposite side of the transversal. So 4 and 6. Angle 4 and angle 6. And lastly, we've also got 3 and 5. What appears to be true from this picture? What appears to be true about all of these pairs? All right, so 3 and 5, 4 and 6, 7 and 1, 2 and 8. What appears to be true? They look like they're all congruent to each other, right? And in fact, they are. It's a feature of Euclidean geometry is that as long as those two given lines are parallel, R and S, then these pairs of these angles that we've labeled are always going to be congruent to each other. So I'll label this as two separate theorems, even though it's sort of if and only if in our case. So I'll tell you why in a second. So 2 theorems. First up, if R and S are parallel, then all pairs of alternate and corresponding angles are congruent. Right, and I've drawn R and S so they're parallel, so it looks like for us, it certainly looks to be the case that this theorem is true, at least in this drawing, that no matter which pairs of alternate or corresponding angles you choose, they're always congruent. So that's a theorem. And the converse is also true. And in fact, you don't even need as much. For the converse, all you need is a single pair. If you can find a single pair that's congruent, then all of them are. And therefore, R and S are parallel. And so if a pair of corresponding, I've gone with alternate in the first thing here, so we'll go that order. If a pair of alternate or corresponding angles is congruent, then so are all pairs. And RNS are parallel. So sort of an if and only if statement, right? If your lines are parallel, then your pairs of these angles are always congruent, and vice versa. If your pairs of angles are congruent, then the two lines are parallel. The reason I've separated them and not written as an if and only if statement is because this first one is only true if you assume the parallel postulate, right? This fifth postulate of Euclid that gives us Euclidean geometry. If you don't assume that parallel postulate, the first theorem is not actually true, but the second one always is. So this will be an issue for us in geometry too later on down the road, is that this is actually true in all neutral geometries, hyperbolic geometry, Euclidean geometry, and so on. But the first one isn't. So I've sort of written them separately, because this one is actually more general in some way than the first guy. Not something we need to worry about right now. This is a class on Euclidean geometry, but it will pop up eventually. I'm not going to prove this. Let's label one more pair of angles. And in fact, I don't even need a transversal to label these angles. It's not true just for transversals. So suppose I just have one line, S, and another line that cuts through a T. That always creates four angles, right? 1, 2, 3, 4. And in this case, 1 and 3 are called vertical angles. They're sort of opposite each other. And 2 and 4 would be called vertical angles. They're opposite each other. So vertical angles let's not write a description. Let's just tell you exactly what they are. 1 and 3, and 2, and 4. And my claim, I don't think our textbook proves this, but the proof is very simple. So we'll state this as a theorem and prove it. Vertical angles are always congruent. Vertical angles are always congruent. So actually really simple to prove this. A few other definitions I haven't made, but I'm sure you know them already. Complementary angles, angles that add up to 90 degrees. Supplementary angles, angles that add up to 180. So for example, angle 1 and angle 4, those are supplementary, right? So we'll write a very, very shorthand, lazy proof, I think. Angle 1 plus angle 4, that's 180 degrees. What do angle 4 and angle 3 add up to? They're also supplementary, right? So also 180 degrees. And angle 4 plus angle 3, that's 180 degrees. And I think now, what do I want to do? I think I want to substitute. What does angle 4 equal? That means angle 4 is 180 minus angle 3, right? So I'm going to substitute that back into the first line. So we've got angle 1 plus angle 4, which is 180 minus angle 3, equals 180. So quick little bit of algebra here, subtract 180 from both sides, move angle 3 over. This of course implies that angle 1 is equal to angle 3 in measure. So those two angles are, these two vertical angles are congruent. They're equal to each other in measure. So I've only proven that this pair of vertical angles is congruent, but you can do the exact same trick with substitution to prove the other pair works. So I won't bother, I will just write similarly, angle 2 is equal to angle 4. And again, I haven't invoked the parallel postulate here or anything, so this is sort of a general result in all geometries. Any questions? All right, so we'll actually do something interesting with this. Now that we have labels or names for these things, facts about congruence and whatnot, we'll do something with triangles. Because triangles are the most important geometric shape. Maybe circles are, but anyway. We've got, let's go back to triangles. And I'll just draw a picture. Here's a triangle. A, B, C. And what I'm going to do is I'm going to extend this side. Something I'm allowed to do, Euclid bothers to postulate this, that you can extend lines. So I'm just going to extend it to some further point D. And that gives me an extra angle that I didn't have before. Right, before I only had these 3 interior angles. Now I've got this angle right here, which is an exterior angle. So this is the exterior angle at C. And relative to this exterior angle, I've got this angle here that I'm not going to care about right now. Of course, this angle and the exterior angle of C are supplementary, but these other 2 angles are called the remote interior angles. Or the opposite interior angles they're sometimes called. So that angle and this angle are the remote interior angles. And of course, depending on which ones are remote depends on which exterior angle you're looking at. So this would be, of course, with respect to the exterior angle at C. All right, so we're going to make a statement about exterior angles. Here's our theorem. This is sometimes called there's 2 different versions. This is the strong exterior angle theorem. So, do I want to go with the strong version? Yeah. We'll call it the strong exterior angle theorem. Again, I'm not sure our textbook bothers to specify that this is a strong form, but it says the following. It says an exterior angle of the triangle equals the sum of the two remote interior angles. And moreover, that immediately tells you that the angle sum of the interior angles of a triangle must be 180 degrees. And I'll show you why that's true as well. So also, the sum of all of the interior angles of a triangle is 180 degrees. So why is this called the strong form? Well, because I think it's postulate 16, very early on in the elements, Euclid proves a version of this. It's not quite as strong. It's called the weak version. He shows that this exterior angle has to be bigger than either of the two remote interior angles. He also messes up his proof. It's the first example, I think, of his first flaw in a proof. But yeah, so he proves that this angle here must just be bigger than the other two. But if you go a little bit further, then I think it's postulate 29 or something, further on down the road, he proves a stronger form where this exterior angle is actually equal to the sum of those two angles, which is the form we have here. And it's sort of interesting why he does that, right? If you can prove this stronger version, why prove the weaker version to start with? And no one really knows. But it's interesting that to get the weak form, he doesn't use the parallel postulate at all. It's sort of like he's hesitant to use it, which is interesting. Like he realizes there's something odd about the parallel postulate. Maybe not. Maybe he just wanted to do it the hard way. But you can prove the weak form without relying on the parallel postulate at all, which means the weak form is true in other geometries, hyperbolic geometry and so on. We'll prove this. So again, I'm just going to write down my labeling scheme and everything. Consider triangle ABC. Consider triangle ABC as shown. So I'll draw a picture in a second. And extend side BC to a point D. And also, I'm just going to get everything up here one time. Let T be a line passing through the vertex C that is parallel to side AB. Okay, so here we have ABC. We've extended it to the side D to give us this vertical angle, or sorry, exterior angle. And what's one thing we're allowed to do in Euclidean geometry? Remember, this is the parallel postulate. If I have a line and a point not on this line, then there exists a unique parallel line through this point that's parallel to the original, right? So I'm saying let's take a line through C, T, that's parallel to AB. So I'm allowed to do that. Moreover, I want to choose a point. I want to choose a point on this line that lives somewhere around there. So usually I'd just say let P be as drawn or something, but I'll try to specify a little bit more precisely than that. So also, let, oops, I didn't label my point P. Let P be a point on T and this is where the language gets a little bit awkward. It doesn't matter where it is on T. I just want it to be on the same side of BC, or rather BD, whatever sides mean, as A is. So I want it to be up here and not down here. So on T, that is on the same side of BD as A. So as shown. If describing exactly where you want your point to be gets a little bit tricky, just be lazy and say, it's where I want it to be in the figure. Okay, so now what can I say? Let's see. This angle here, and this angle there, what are those? Well, imagine these are two infinite lines, right? AC is a traversal of these two lines, this line and this line. So what are these? These are alternate interior angles, right? Which means they're congruent to each other, as I've drawn. So now, angle BAC and angle PCA, or want to go in that order? Let's go ACP, we'll label it the other way. Angle ACP, these are alternate interior angles. These are alternate interior angles, so they're congruent. And what about this guy and this guy? I'm working with a different transversal, right? Here, this is my transversal to conclude something about those guys. With these two angles, I'm looking at this transversal for these two lines. These are corresponding angles, right? And angle ABC and angle PCD are corresponding angles. So the conclusion is that because these two lines are parallel, because AB is parallel to PC, these pairs of angles that we've labeled are congruent to each other, or to each other as pairs, right? Not necessarily the pairs are congruent. So because AB and CP are parallel, it follows that these are congruent pairs. And I'm running out of time here, so I'm going to wrap this up in one line that actually does the whole thing all at once, I think. I'm also running out of space, so we'll finish this up here. But now what do we have? What's the sum of those three angles? Well, they're supplementary, right? So they must add up to 180 degrees. So now angle BCA, or let's go ACB, angle ACB plus angle ACP plus angle, how have I labeled it here? PCD, that equals 180 degrees, right? All three of these angles, because they're linear or supplementary, that's 180 degrees. And by substitution, we have, well, this angle here, ACP, can be replaced with this angle at A, right? So angle ACB, which is this interior angle, plus ACP, we'll replace that with this guy, which is angle, what have I called it? BAC. Which is this interior angle here, plus last but not least this guy, which is congruent to this angle, this interior angle, plus ABC, angle ABC equals 180 degrees. Or if you want to label this more clearly, this says angle, what is ACB? ACB, angle C plus angle A plus angle B is 180. I'm changing the order here, but that's exactly what we wanted to prove, that interior angles sum up to 180. Admittedly, I skipped a step in the interest of time because we're going over time. We didn't actually prove that the exterior angle summed up to these two guys, but it's an immediate jump from here. In fact, we've leaped over it. We just went straight to the conclusion that the angles of a triangle add up to 180 degrees. So I wanted to take your seating positions today, but it's okay if we do it on Monday. So I will do that on Monday. Sit where you want to sit, because that'll be your seat for the rest of the semester. I will post up homework either tonight or tomorrow sometime, and it'll be due a week from today. If you don't have the textbook yet, I'll type up the problems as well, so you can at least have the problems. Have a nice weekend, guys.